In problem 2.3, part A, we are told that for the case of equal roots of auxiliary equation, so let's first write down the auxiliary equation, which is what we get when we solve this differential equation, assuming a solution of this form. Now this will give us s squared plus ps plus q equals 0. So this is the auxiliary equation. Now we are told that in the case of equal roots, this can have two possible roots where s1 equals s2 equals s. So let's, before we actually continue the question, let's actually take a moment to see how this happens or what this implies. So when this equation has two roots that are exactly the same, what are those roots going to be? In general, for a quadratic equation of the form ax squared plus bx plus c equals 0, the roots are of the form minus e plus or minus root b squared minus 4ac divided by 2a. Now for this particular quadratic equation, s is going to be of the form minus p plus or minus root p squared minus 4 times 1 times q divided by 2. Now here the first root s1, let's say the first root is this. The second root s2 should be this. The fact that s1 equals s2 implies this, right? So let's cancel out the 2's, and the negative p also gets cancelled out on both sides. That implies 2 times root p squared minus 4q equals 0. Or p squared minus 4q equals 0, and p is equal to this. Now that we know p in terms of q, what we can do is, let's try to find out what s is. So we know s is minus p plus or minus root p squared minus 4q divided by 2, right? We actually didn't need to solve all of this, to be honest, because we know that this particular term is equal to 0, right? So this is equal to 0. That implies s is equal to negative p over 2. So the equal solutions s1 and s2 are actually equal to negative p over 2. So in the case where we have the two roots of the auxiliary equation to be the same, we have found only one independent solution. We will obviously have only one independent solution because both the roots are exactly the same, right? And that solution would be e to the power sx. That would be the solution. Now we are asked to verify that x times e to the power sx is the second solution. So we need to verify this. So the best way to verify it is to actually solve the equation. which is given by this qy, sorry. Now, in our case, y is equal to x times e to the power sx, right? This is y2. Y1 is e to the power sx. Now, let's solve this equation in terms of y1. Let's first solve it with this, right? So this will give you s squared times e to the power sx plus ps times e to the power sx plus q times e to the power sx equals 0. Now I'm going to go ahead and call it a. Now let's try to do this for y2. For y2, let's first get the first derivative of y2, which will be x times s times e to the power sx plus e to the power sx. The second derivative will be s times e to the power sx plus x sx times e to the power sx times derivative of this is going to give me another s. Now I'm going to plug these two in into this equation, and that will give me all I did was I plugged in the values of y2, the first derivative of y2 and the second derivative of y2 into the linear differential equation. Now here, I'm just going to go ahead and cancel out all of the s squared terms and cancel out, I'm sorry, I should have done that. Yeah, I just canceled out all of the e to the power sx terms. And this can be written as s plus s squared plus s plus psx plus qx to be equal to 0. Now I can club these two and write them as 2s plus p. I'm going to club those two together plus, now I'm going to take this as squared, s squared plus psx plus qx equals 0. I'm sorry, you have an s squared x here. I missed out the x there. There was an x here, so this will be s squared x. Now, I'm just going to keep this 2s plus p here, plus I'm going to pull this x out of everything here. So that will give me x times s squared plus ps plus q equals 0. However, s squared plus ps plus q equals 0 is what we will get when we use e to the power sx as a solution, right? So when we have e to the power sx as a solution, if I cancel out all of these values, the auxiliary equation is what we get. So this entire term is actually equal to 0. So this simplifies to 2s plus p equals 0, right? Now let me take you back to here where we found out what the value of s is. It's negative p by 2. So I'm going to plug that in. The 2 and the 2 get cancelled. You have negative p plus p, which is equal to 0. Okay, so I actually want to make a correction. So when we were trying to prove that the y2 is a solution, I plugged in the values and I actually equated it to 0, which is not something we are supposed to do because we don't know if that is 0. So it was a mistake on my part to equate it to 0. So we should not have that anywhere here. all we do is plug in the value and solve for it. And if we end with a zero, it means it's a solution. That's how we're supposed to do it. I should not have put the equal to zero there. So when we solve it, we clearly show that it actually is equal to zero, therefore telling us that this is in fact the second solution. So hence we have verified that part. Now in part B, all we have to do is we need to solve the differential equation. Let's assume y is of the form e to the power sx. So that's going to give us s squared minus 2 times s plus, plus 1 equals 0. If you want me to show you how we ended up with this, we can actually just plug in the values and check. It's going to be s squared times this times I'm just going to cross these out. Give me s squared minus 2s plus 1 equals 0. Now, this is nothing but s minus 1 whole square, right? So we have two equal solutions, 1, comma 1. Now, from part A, we saw that if y1 is e to the power sx and the auxiliary equation has two equal roots, then y2 is of the form x times e to the power sx. So in this case, the solutions are going to be y1 will be e to the power x and y2 will be x times e to the power x. So these will be the solutions. Now that we have the two solutions, the general solution is going to be a constant times y1 plus another constant times y2. So this will be the general solution.